the values at the children. So those are the two properties there for part B. What about C? We've got this. So we've got these kind of dual competing pictures of the heap. One is this complete binary tree. And the second picture that we have is that we're partially filling the array. We're not using index 0, so that's out, but we're using index 1, index 2, index 3 through our last index, index end out here. So we're using this and this and this all the way from index 1 up to index n. Those are the places that we're using. And so there's a question about, so index 1 is the top of the heap. Indexes 2 and 3 are the next. So what's actually stored there? If there's a 5 stored here, then I've got a 5 here. If index 2 has a 4 in it, and index, okay, so index 1 has a 5 in it, index 2 might have a 4, index 3 might have a 1. So it might look like this. And the question is, what's the highest index that has a child? What's the rule? How do you find a child? Well, take a look here. Node 1, the root, has for its left child 2 and for its right child 3. What's the rule? You double, right? You double. And so the very last node, so the index here is end, okay? So the very last node has index end, and what's its parent? Its parent would be end divided by 2. So, so end divided by 2 would be this guy. End divided by 2. Again, you throw away the fractional part. And so what about these nodes here? They don't have any children. Okay. So end over 2, this is the last node that has a child. The next node can't have a child because the next node, when I take 2 times this, it'll be larger than this. 2 times end over 2 takes me back to end. Yeah? Okay. So end over 2, this is the last node that has a child. There. Part D, given an index I, so again we're using this model, but we're referring to this thing over here. If we are at index I, so here's 0 that we aren't using, here's index 1, somewhere up here I've got index I, and where's its right child? What's the formula? To find its right child, it'll be at index 2 times I plus 1. So the right child of I is 2 times I plus 1. That's part D. So I'm not, I don't think these should strain you too much. You're supposed to write code now in part E that, so this was what? This was D. What is the index of the right child? So part E, we're supposed to swap. We're supposed to write code. So in general, you're swapping these two, but here for part E, you're supposed to swap basically A brackets I and A brackets J. So yeah, I want to take the value here and put it over here. But if I do that, that wipes out the value that's here. So to do the swap, I guess we're assuming first of all that this array is an array of integers, and that the name of the array is A. So I'm going to say int. So this is a place for a temporary value. So we'll say down here temp is going to be equal to a brackets I. So I'm saving the value in a brackets I. And now that I've done that, we'll put a bracket, the value that is in a brackets j, we'll put it over here at index I. So that's part of the swap. And then what do I want to do? The last line, I want to put in j the value that used to be in I. But it's gone now here. It is, but we saved it up here, so we say 10. So this is a way to accomplish the swap. There are other ways to do the swap. This is probably the simplest. So I was expecting to see in a code something like this for part E. Are there questions on this?
J's the end value, right?
What?
J's the end value.
It might be the end value. I mean, maybe we're doing another swap. I don't know. But yeah, where it actually appears in heap sort, you're swapping what's the very first item with the very last item. Yeah. So yeah, so I don't know. I would be 1 and J would be in. Right. That's where it's used inside of heap sort for those two. Are there questions on this? What about sift down? What's the most important thing about sift down? So now I'm moving on. I'm suggesting what I might be concerned. What are you doing? You want to fix up. You're at some place in the array. Sift down int I. And so what are we concerned with? Here's index I. And we have this over here would be index 2 times I. If it's in the tree, and this would be index 2 times I plus 1. Left child, right child. We don't have to do anything if the value here is greater than or equal to these two. And so the first thing we need to test is, it would be good to find out which child is larger, because once we have the larger child, I'll just compare the value here. So this is the picture here, and then then we have the picture inside of the array. Again, index 0 that we aren't using, index 1, and then that's filled, and then somewhere here we've got I, index I, and then further on we have index 2 times I, and right next to it, right next to 2 times I, over here, that's 2 times I plus 1. Okay, so here's the picture as a binary tree. Here's the picture in the array. There's one other thing. Where is end? End is somewhere. End could be here, or end could be over here, or end could be, possibly end could be here. So there's a lot of different places end could be. What we need to do is we need to compare the value here with the largest child. And if that value, that's what sift down does. If that value is what? If that value is smaller than the largest child, then we actually carry out a sift down. So we're talking about, what does sift down do?
It rearranges the children.
It rearranges the children. But first of all, you need to find out which is the largest child if you have 2 children. So you start off saying things. So I'm reminding you of the code now. You say, well, if 2 times I, if that is if 2 times I is greater than n, then what does that mean? It means this node doesn't have any children. So void sift down. So if 2 times I is bigger, so that is the left child would be at 2 times I, but if 2 times I is bigger than n, remember, so the picture looks like this, that end is over here, and here's 2 times I. 2 times I is bigger than n. Then node I doesn't have a left child, and so what? It's already perfect. It's bigger than its children because it doesn't even have any children. So we can just return in this situation. So if 2 times I is bigger, then we just return. So what does that mean? We definitely have a left. So if we get to here, what's the situation? 2 times I isn't bigger than n. So what does that mean? 2 times I could be equal to n, or 2 times I is actually less than n. So, but we very definitely have a left child. And to begin with, I want to know which child is largest. So I'm going to say here int largest equals 2 times I. I don't know that it's 2 times. At this point, it's the only child I've seen. So we'll say 2 times I is largest. Yeah. Now we're going to check to see if there's a right child. So if 2 times I plus 1, if that is less than or equal to n, then we have a right child. And what we have to check there, I'm assuming that the largest is the left child, but if this happens, that there is also a right child, we've got to check to see if it's even bigger. So if this happens, and if A brackets 2 times I plus 1, if that is bigger, if the value at this index, 2 times I plus 1, if that's bigger than the index of the left child, 2 times I, then in that case, the largest is going to be 2 times I plus 1. So this is the first shot. We have a left child, so maybe that's where the largest is. But if we have a right child, and if the value at the right child is bigger than the value at the left child, then the largest is this thing over here. So when we finish this piece of code here, what do we know? We've got this variable largest contains the index of whichever child is the largest. But we aren't done yet. We now need to compare the largest child with the value here. Okay, so what's the next stop? Well, we're almost done. That's, well, at least if you're used to recursion. Okay, so I'll continue. I'll continue over here. So if the value at largest, if the value at the largest is greater than the value at I, A brackets I, so we're checking. I don't know which one of these is the largest, but largest now is either this, if this contains largest, or the largest is this if this contains largest. So if the value at the largest is greater than the value at A brackets I, then we need to do what? We need to do a swap. Okay, so then we have some work to do here. We have to do, so we're gonna do what? We're gonna take the value here, move it down here. So I'm gonna say int, so you're used to this, int temp equals A bracket largest, and A brackets largest equals A brackets I. We're doing the swap, and then finally A brackets I equals temp. Semicolons after all. That does the swap, and what else do we have to do? So where's the bad guy? The bad guy was here, and now we've either moved him over here, if this is where the largest value is, or we move this bad guy over here if this is the bad. So what do we need to do now? So now I need to worry about, say I move it here, I need to check out how it is with its children. So what we'll say down here, one last line, we're going to say sift down. This is the recursive part. Sift down, parenthesis, largest. So I've noticed that we've made a lot of progress. We've gone from I to 2I, or even better, from I to 2I plus 1. Whichever one of these did have the largest. That's where the trouble is. That's what we do if A brackets I, if A brackets large, if the child is bigger than the parent. What do we do otherwise if the child isn't bigger than the parent? So if neither child is bigger than the parent, so that's the else here. If the child is bigger than the parent, we do this. But otherwise, if the parent is greater than or equal to its children, we're happy. There's no need to do a sift down. And so that's just the end. The end of sift down. So, I mean, we have to do a little bit of work to find out which child is the larger child. So the larger child is either at 2I or 2I plus 1. And then we need to check, is the value at the larger, we now have the index of the largest child. So what is the value at that largest? If that value is bigger than the value of the parent, we do the swap. And so now the place that did have the largest value, that's the new place that our trouble node might be, the thing that's small. And so we have to sift down from there. So if we do have to do this, here's the sift down right here. We're moving it down and taking what was below but was larger, we're moving it up.
Don't we have a swap function to call instead of doing?
Yeah, you could write a swap function. Yeah, for sure. You could have swap int I, int j, and what does this do? We're going to be swapping this. I won't put it. This swaps a brackets I and a brackets j. Yeah. So you supply the indices, and then those two places in the array are swapped. Yeah. And that would be good because we do that over and over. So the sift down, each time sift down run, it moves this small value here down to one or the other of the children. Yeah?
So is this like I'm getting hung up on whether it's a top-down or bottom-up approach. Is it a top-down?
Yeah, we were working from the top. I mean, this is not, usually when you use those terms, you're talking about developing code, where you kind of, a top-down approach is you kind of have what the general big steps are, and then you go back and you fill in each of the big steps with more detail. Yeah, that's a top-down programming approach. But here, it's top-down in the sense that we put this bad guy all the way up here at root. It starts off at 1. So when you run that sift down, you're doing sift down parenthesis 1. But sift down parenthesis 1, node 1 has 2 children. 2 times 1 and 2 times 1 plus 1. It has these 2 children. We're going to check to see, is this value that we just put, that we put here, we dragged it up from the bottom from in and put it up here. We want to check to see, is the value at 1 greater than, if it is, we get to stop, but if not, we'll pick out whichever of these is the largest, move that up and move the value at 1, put it in place of whichever child is larger. And so what that does is that moves the troubled node to either node 2 or node 3.
Mm-hmm.
And then we have to run sift down from there on that node. So this is, it's more complicated than the selection sort, but I think it's fairly understandable. I mean, sift down also gets used, what? It gets used to build the heap originally, to make, to, you always have this, you get this shape for free, but when you start off, we want the parent, each parent to be greater or equal to the values of its children. And so you use
Yeah.
sift down there
It
also.
seems to me like when you're passing the largest value
Yeah.
back to itself in a new call, it seems like you're only working one side of the tree. Am I wrong in saying that? Because if it's going to start at the largest value and compare its children, right? It's only going to be working part of half of the tree. What about the other nodes? Does that make sense?
I'm not, okay, so this is what,
Like, for
see,
example,
this largest could be the left child, or the largest could be the right child.
Mhm.
The largest is which, if I look at this value here and this value here, and whichever one of these has the largest value, that's the largest, right? If the right child, if the value at the right child is bigger than the value at the left child, then the largest is.
Yeah, I get it. So you're gonna
Okay.
start at the largest in the second call, right? So
Yeah.
what about all the rest of the children that are on the other child's? No.
Okay.
Does that make
So,
sense?
yeah. So let's talk about that. So we've got the thing, this tree.
Mhm.
Let's say the tree looks like that. So what's just missing are, so this thing right here, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ha, unlucky 13. This is index 13. Okay. The first thing that we do is we make sure that you get the heap shape, this shape, you get that for free. But when you build the heap, you make sure that when the heap is built, that this guy is greater than or equal to these two. This is greater than or equal. So we've got this other property that each parent is greater or equal to the values of the children. So when you do the swap, when I take this value here and move it up here, I take the value that was up here and move it down here, and then this is no longer, well, I no longer have to consider that as part, so the heap is, so this is now where the maximum value is, and I don't want to mess with it anymore. So the heap grows one smaller. Now, where's the only bad node? The only place I made a change, so this is no longer in the tree, so it's not bad. But we did take the value that was here and put it up here. So this guy may not be greater or equal to its children, but this is still greater than or equal to its two children. This is, so the only bad node, is here at the top. So I only run sift down when I'm having, I only run sift down from a node that might be bad, that where the value, this value may not be greater than or equal to the value of its children. But see, this guy is already good, and this guy is already good, and so if I do one step of that sift down, then look at what I'm doing. I'm taking whichever child is bigger and putting it up here. So if I say, if this guy here moves up, it's because it's the larger child. So when I move it up here, it'll be bigger than this child, and the only reason I'm doing this is because this guy is bigger than this. So when we get through with this thing, the value here being up here, it'll be bigger than this child because I took the bigger of the two children. And the only reason I'm doing this was because the parent wasn't bigger. So the parent will be down here, and the parent value is less than this. So this node is fixed.
Yeah.
All of this, I haven't messed with any of this. So this guy is greater than or equal to this. And so the only possible place that's bad right now is this guy may not be greater than or equal to its children. If it is, I'm done. If it isn't, then I'm going to either bring it down here or bring it over here. And so if I bring it down here, I'm bringing it down in place of the big, let's say I bring it down here. If it ends up being brought down here, I'm bringing it down here because this is the bigger child. So this is going up here and the P is coming. So the bigger child is up here. It's bigger than this, and it's bigger than this value that was here. So this is now fixed, and now I just have to worry about this. So you either end up moving it down so far that it's greater than or equal to its children, in which case I'm done, or it's all the way down here and it doesn't have any children. That's a good, don't have children, you don't have anything to worry about, right? Children. Okay, so the situation is there's anytime when you do the sift down, you aren't messing. So I took the larger of the two children when we said it was here. So when I moved that up, that wasn't going to mess with this right-hand side because since it was the bigger child, it's already greater than or equal to this. And this is already greater than or equal to this. I mean, the only bad...
How do we know that already? That's what I'm getting caught up on. How do we already know that?
So the first step, right, is to build the heap.
Yeah.
And so when you get through with that first step, you have it perfectly that every node, every parent is greater than or equal to its children. That's what that's what building the heap is.
Okay, I get it now.
So it's, and so then the only problem comes in when I take this little tiny value here and move it all the way up here to the root. And so there's really no reason for this value that was down here for it to be greater than or equal to its two children. But everywhere else, so the idea is that there's only one bad place. And so let's talk a bit more about building the heap. So let me put a tree here. Say this is the tree. The place that, so how do you what's the first so let's see, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So in this picture, end is 11, and so end over 2 is 5. And so the first node, see, I don't have to worry about nodes 11 and 10 and 9 and 8 and 7 and 6. None of those nodes don't have any children. So I don't have to worry about this property that the parent needs to be greater. So the first node that I have to worry about, so I'm working, this is bottom up. Okay. The first node that I have to worry about is the node at index 5, end over 2. So this guy has at least one child, and if it were like this, then it has exactly one child. So it's got at least one child, and what we need to check is it greater than or equal to its children? If it's not, then we run sift. What we're going to do here is we're going to run sift down. We're going to run sift down of 5. So that's what building the heap is about. For I equal end over 2, I greater than or equal to 0. Oh, sorry. Yeah, greater than or equal to 1. I minus minus. So we're doing the. What are we going to be doing? We're going to be doing sift down, parenthesis I. This is building, this builds, so sift down is the key to everything, it turns out. We need a semicolon here. So we're starting off right here at node 5. And so what do? What does sift down do? It looks for the bigger of these two children, and if the value at 5 is greater than or equal to the value of the larger child, then we do nothing. Everything is fine. But otherwise, we do a sift down. And so we'll sift 5 either down over here or over here, and we'll take, if I do it this way, this guy moves up. If I move 5 this way, then this guy moves up. And then we can say that the subtree rooted at 5 is fine. The value here will be greater than or equal to the children. And so we move on to 4. So that's what this is doing. After I do n over 2, which is 5, we do I minus minus. That's still greater than or equal to 1. So we were here at 4. And so we run sift down again from 4. So we have to do one swap to fix this guy up. We might have to do one swap. We have to do one swap to fix this guy up. And after we do 4, I minus minus, so then we're at 3. We have to do one, we might have to do, maybe this is greater than or equal to these things. We don't have to do a swap. At worst, it's one swap, one swap, one swap. When I get to here, node, so now I'm looking at the subtree based at 2. And so it may not be greater than or equal to the values here. So I might have to take the greater of these two and move it up and move this down. So the point is, there's only one bad place. We've already fixed up the tree rooted at 5. We've already fixed up the tree. So this is already a maxi. This is already a maxi. The only possible bad place is here at 2. So that's sift down's forte, is that you give it a value that might be bad and you might have to swap it down. So it might get swapped here and then here, or it might get swapped over here, then here. So here I might have to do as many as 2 swaps to fix this guy up, but sift down calls itself. So when we do sift down 2, when I equals 2, the value here may get swapped either here or here. Then we recheck. Is the value here greater? If it is greater than or equal to these 2, we're done. If not, then we take whichever of these 2 is larger and move it up. So sift down always works at a place where there's just, the root is bad, but everything else is okay. Remember, it started off at 5. The root might be bad, but these 2 things are okay because they don't even have any children. So you run sift down only when what's bad is at what might be bad is what you give it. So yeah, 5 might be bad, so I have to swap it down. But these by themselves are good because they have no children. Same thing for 4 and 3. When I finally get to 2, yeah, this could be bad, but we've already run sift down over here on 5 and 4. So when I get to run sift down on 2, I'm running it for where this is fine and this is fine, so the only bad place is 2.
Right, so when you swap the value, couldn't it mess up one of the already perfect maxi?
Well,
Like you swapped
yeah.
it before and that caused.
So let's say we swapped the value at index 2 and the value at index 4. Yeah. So remember, I said 2 swaps. So what is
Okay.
sift? See, what is sift down 2? Its last step was that if you have to do a swap, then you run sift down on the place that you swap to. So if I'm swapping the value here to its left child, then I'm going to run sift down from here. Well, and the first step of sift down is to compare the value here with these 2. If it's okay, then I'm fine. But again, so what are we doing? We're moving our trouble down.
Okay.
Yeah.
I get it.
So it's kind of nice. It's sift down is used in this very simple way here, and then sift down, and then it's also used for the sorting part. Okay, so I mean it's worth your while to know heap sort. Among other things, it's fast. If the number of nodes you have is n, then it's n log to the base 2 of n. So it's not n times n. That's the selection sort. So what does that mean? The number of comparisons that you're doing here for selection sort is, so if I have n items, in the selection sort, I'm doing roughly n squared comparison. N squared comparison. On the other hand, if we're doing heap sort, so we aren't doing the selection sort, or we're doing the heap sort, then instead of having n times n, it's n times the log. Now log is ugly. You don't like log. Lots of you don't like log. I think log is okay. What is log to the base 2 of, I don't know, 32? This is not a mysterious thing. What exponent do I have to put on 2 to give me 32? What's the answer?
5.
It's 5. So the log, so since the exponent is a 5, log, so the point is exponents grow much slower. So if I double 32, I get 64. Things have gotten twice as large, but this will just go up by a 1. Twice as many nodes, but just one more, the log 2 is just one larger. The formula is n times log to the base 2 of n. So yeah, if I go from 30, so in one case I'd have 32 times 5, that's, and I'm going up to 64 times 6. How does that compare with, so this is heap sort. How does that compare with the selection sort? I'm going, here it'd be 32 times 32, and now I'm going up to 64 times 64, n times n. So notice, what's the increase here? I've doubled the 30, this first 32, I've doubled the second 32, and so this is an increase by a factor of 2 times 2 or 4. Okay, so I've made this point over and over again, but it's worth getting this point. So here, yeah, this doubled, this only went up by 1. So basically, I mean, you can almost ignore that. Basically, you've doubled. It's a little bit worse than doubling, but it's a lot better than what's going on over here. So that's what makes the heap sort better. And so the best sorts that use comparisons, there are some sorts that don't use comparisons. The best sorts that use comparisons then have this n log n, log to the base 2 of n property. It doesn't really make much difference what the base is. That just, whichever base you use, that's just a constant here in front. What you care about is not that the constant would be here and be here, so the constant doesn't really figure into the growth. Same thing over here. I mean, it's probably not n times, you know, maybe there's a 1/2 n squared in front. You know, the constant's 1/2, but I've got it 1/2 here and a 1/2 here, and all I care about is what's the factor. So yeah, there's a 1/2 here and a 1/2 here, so I can forget about it. The increase is a factor of 4. Okay. Other things we might want to talk about. So this test is yeah.
Are we gonna fix eval AXP one?
We've got a lot of work to do on that one. We have, what, 3 more minutes in this class. So, yeah, if you have questions about the test on Thursday, I'll take them first tomorrow, Wednesday. But if not, we're going to work on the eval expressions. Yeah, I really do want to work and get that chugging along and have it evaluate expressions. Yeah. Yeah, no, we aren't close to getting that one done. Yeah. And that's it. I guess I have to turn in interim grades for you. Today is the day that I have to have the grades in by 4 today. I am going to grade something and turn in a value. I would much prefer to have had this test a little earlier. It would be kind of largely my fault. I diddled along a little bit. So I'm going to give you an interim grade, and it may be better than what and then we're going to do the test. Okay, so so the test, we're doing the test, Thursday? I will attempt to have that back Friday, and that should be your best indicator of how you're doing it, better than the interim grade that I have to give you by 4 today.
You said this Friday? We're not gonna be here.
That's right, we aren't. Hell, okay. Tuesday. Or I can mail it, how about that? In Blackboard, I wanna get this test graded and back. Yeah, you don't believe me, okay, well, that's, so, you will get to see your test grade, and then on Tuesday, you can argue with me about your test grade, or you can say, I'm very happy, that'd be nice. I'm hoping, yeah, that you do well. Yes,
Just one more time, what are we gonna have in the test again?
so the test is gonna be divided into two parts.
Okay.
You get to see the whole test. The first part of the test, you're writing it out on paper. You don't get to use the computers. You don't get to use notes. You're supposed to just use what you know. We've spent time talking about what's going to be on this test now. I don't know. Maybe we need to spend more time talking. We could do a recursive example tomorrow before. And okay, so you do that. You do that part. You can spend as long as you want onto that, but you only have 50 minutes. And whatever time you leave, that's the time that you'll spend writing a program that is the second part of the test. You'll get to see what the program is. And once you kind of, it'll maybe be on 2 pieces of paper. You hand in one piece. You'll get to see both pieces. You hand in the first part, and then at that point you can start, doing your work on the computer, and you can use notes and so on. Yes.
So if we feel pretty solid on like what you've given us in like run times and recursive, like is there anything else that we should look at or?
No, I think the run times, the recursive, which maybe I'll talk just a little bit more about tomorrow, and the selection sort and the heap sort, then you should be okay for the test on Thursday.
So can we have a, I don't know, like a sheet we can review?
Well, I passed out. I did pass out. The questions on selection sort and heap sort, and before that we also did some run times. So I don't know if you want some more. You want some more practice on run times? Yeah.
Did you grade the run times?
No, I haven't graded those yet. I will. Only two people handed those in.
Oh, gotcha.
Okay.
All right. I just don't have that to look at.
Yeah. I'll see if I can get that back to you tomorrow.
Okay.
I haven't lost it yet.
I'm very good.
But maybe, if it goes another day, yeah, it could disappear. Other questions? Okay, so, yeah, you should study, but on the other hand, if you don't get sleep and you come in all nervous, that's not good. If you want to talk to me, I do meet my office hours. I have office hours right after this. In fact, this is office hours start in 8 minutes. I would be glad to see you then, or if you can't come then, I can see you some other time today or tomorrow. I would be happy to talk to any of you about what your concerns are. Okay.